one more concept. We need a basis for choosing the velocity gradient, how fast we're going to deform the fluid in the flocculator. And the question is, what happens if we have very high values of G, where we're deforming the fluid really fast? So it looks like it would be great. So I do the example there of if G were 10,000 Hertz and GT were 35,000. So we use a GT of 37,000 in agua clara, but there I use 35,000. If we had a G of 10,000 Hertz, we could have a teeny tiny flocculator with a resonance time of 3.5 seconds. Because in those 3.5 seconds, we would have deformed the fluid so that particles that were separated by a millimeter had moved 35 meters apart by the time the process was done. It would have required lots of energy, actually an absurd amount of energy, 36 meters of head loss to drive this flocculator. But it is kind of cool that you could have a flocculator all done in 3.5 seconds. But there's another constraint. So there's another reason why we can't actually do this. And that is that the flocks break, or maybe better said, they don't actually form and don't grow large when G is very high. And so we need another concept. So this is the model. If you have a flock sitting in a velocity gradient, that flock is rotating and it's experiencing forces that are trying to pull it apart. So at the top of the flock, the water is moving to the right. At the bottom, it's moving to the left. That's causing the flock to rotate. And that means, okay, so there's actually shear on the flock at the top that's pushing it to the right, at the bottom to the left. Because the flock is rotating, that means that the fluid is actually pushing down on it on the left, and the fluid is pushing up on it on the right. So those last two arrows are because the flock has been forced to rotate by the fluid at the top and the bottom. Because of that, it's traveling, the flock is traveling up. Can I rotate this flock? Let's rotate this flock. There it is. Okay, so that's the flock rotating. And so if we go back, because of its rotation, it's experiencing those additional forces on the left and the right, shear forces. And that means that there's a compression plane where if you look at the arrows, they're converging on that plane. And on this tension plane, the flock is being pulled apart. So the flock is not going to fail in compression. Things usually, well, buckling happens in compression, but the flock is not going to fail in compression. It's going to fail in tension. That's when one of those little coagulant nanoparticles gets pulled off of a clay particle because the bond wasn't strong enough. So there's a tension plane, and that flock, if the velocity gradient is high enough, the tension on that tension plane will be large enough to break it apart. So those are the 2 points where this flock is held together, and there's one coagulant nanoparticle bridging between those two pieces. And remember, the reason that this is happening this way, why there are just 2 or 3 places where these flocks are held together, is because this flock formed by having 2 similar sized flocks joined together. And when they joined together, they were at most 3 points of contact. So that's why there's so few coagulant nanoparticles actually holding this together. And so we're going to get this amazing event where it breaks apart. And it broke apart because those coagulant nanoparticles couldn't resist the force of shear. And that means there must be some equation that ties this together. And indeed there is. This is, I forget where, but we pulled this out of the literature somewhere. This is an equation that describes the force of shear on a sphere. And that F bond is the force that's trying to hold the sphere together at its hemisphere boundary. And this tells us that if we increase G, D is going to decrease. Okay? And why might that be a problem? If we, so remember, we're talking about why don't we make a flocculator that has just a really, really high G? And the question is, what goes wrong when a flocculator has a really, really high G? And what we see is we're going to not be able to produce any big flocks because they're going to be torn apart or prevented from forming, one of the two. Why does that matter? Oof. Because the flocculator has to produce flocks that settle fast enough to be captured by the plate settlers that are coming up. So I know we didn't talk about this yet, but just take it on faith that we're going to be able to capture particles based on how fast they settle. So that means we need to produce a flock that settles fast enough to be captured by the plate settlers. So we're going to combine two ideas. And I am so excited about this because this is a new derivation that happened like in the last 3 weeks. Okay, so this is about as close to real time as you typically would get in a class. So we're going to take that one equation and we're going to combine that with a previous equation that we had, which is the sedimentation velocity of flocks. So we had this equation that takes into account the fractal dimension of flocks and the fact that they're settling like a low density sphere. We can just put those two equations together and we can make this this additional assumption that the capture velocity is a property of the plate settler, and it's how fast a particle has to fall in order to be reliably captured by the plate settler. That's the capture velocity. So we'll set the terminal velocity of the flock to equal the capture velocity of our plate settlers. And I forgot to mention one more big assumption that's in here, and that is I assumed that the fractal dimension was 2. It's close to 2. We're still figuring out exactly what it is, but it's very close to 2. So I made that assumption to make it so that I could do some easier math. And we get this relationship between velocity gradient. And I don't know if you noticed anything that's crazy about this equation, but let's look at this in the next page. In this equation is G, the velocity gradient in the flocculator. There's nu, which is the kinematic viscosity of water, which is a function of water temperature. And do you see the exponent on that nu? I have never seen nu cubed before. And it's because we're combining two different effects where nu is important in both of them. Nu is important in ripping flocks apart that are in shear, and nu is important in determining how fast flocks settle in the sedimentation tank. And so nu enters the equation twice, and because of the fractal dimension, it ends up being cubed when it's done. And this explains something that has been a mystery for a very, very long time, and that is why is flocculation and performance of a water treatment plant so strongly influenced by the effects of temperature? And this equation tells us why. It's because nu is cubed in this equation. And so the little change in viscosity that might be a factor of 2 between 20 some degrees Celsius and 0 degrees Celsius ends up being a factor of 8 in this equation. And so this is hugely important. V sub c is this capture velocity, and that term is squared. And I took this one step further. And okay, so I plotted it, and I looked at, I have one data point on this graph, which means that we are begging for some more research. The one data point was done by Casey Garland. It's a purple data point that's out there around 22 degrees Celsius because she did experiments at room temperature. And so that was the curve that she was on. And what I'm showing is based on this model, the maximum velocity gradient that you can use in your flocculator, given a capture velocity that you have in your sedimentation tank, the maximum velocity gradient plummets as the temperature drops, which means that if you're designing a water treatment plant that's going to have to treat both cold water and warm water, what matters is the cold water. It's the cold water that's going to be hard to treat, and you have to make sure that you design your flocculator with a low enough velocity gradient so that the flocculator will still work when the water is cold. So I decided to invent a new symbol, and I admit that I must have spent like 8 hours trying to figure out how to do this, because I like dimensionless quantities, and I couldn't figure out any way to make a beautiful dimensionless quantity for this parameter, because this parameter, which I'm calling zeta, zeta describes a whole bunch of flock properties. And flock properties and the coagulant properties. So it's the force of the bond of the coagulant nanoparticle, it's the diameter of the core particle, it's the density of the core particle. All of that is tied up in zeta. And once you know zeta for a particular suspension, that then can be used to guide the design of the plant. So zeta is like this intermediary. It is a function of the flock properties, and then it can be used to design the plant. And it means that G in the flocculator times the viscosity of the lowest water temperature that you have to treat cubed times the velocity, the capture velocity squared in the plate settlers, at most, when multiplied together, can be zeta. A lower value is great. A higher value will lead to failure. Zeta is a function of the core particles. And if the core particles include lots of dissolved organics, that is going to lower the density of the core particle that you're trying to flocculate. So the core particle is what comes together first. It's like the clay particle plus some coagulant nanoparticles, and maybe those coagulant nanoparticles have some dissolved organics attached to them. So that mess of three things, a clay particle, coagulant nanoparticles, dissolved organic molecules, all coming together, that's your core particle. And the density of that multiple component particle decreases as you add more dissolved organics to it, because the dissolved organics have a density very close to water, maybe even less than water. So they're lowering the density. And so if you have a water with lots of organics, your zeta for the water you're trying to treat is much lower. And that's going to change the design that you can use for the flocculator and the sedimentation tank. So why is this a big deal? Every time previously when I taught about flocculation and sedimentation, and somebody would say, but what raw water quality, how do you use raw water quality to adjust your design? I would say, it doesn't influence the design in any way. But now I know it does. Temperature is huge. I knew that there was a temperature effect before, but I didn't know that it was so significant. And if you've got a water that has dissolved organics in it, you have to change the design for the flocculator and the sedimentation tank to account for that. And these are the equations that describe how that is done. I will remind you that I only have one data point on this graph. And so this model is like based on physics, one data point. We would like to confirm it. The reason that I think it is very likely that we are on the right track here is because the values of the velocity gradient that we get for close to freezing are similar to what is actually used in the design of water treatment plants here in the United States. And so it makes sense. Whereas I was completely baffled before because Casey had done these experiments and her purple dot is up there at like 500 Hertz. And it suggested that we could operate at 500 Hertz in a flocculator before we would start seeing deterioration in performance in the sedimentation tank. And that's what she observed. But she was operating at room temperature at 22 degrees Celsius. And so if we take her results and work it down to cold temperatures, then all of a sudden we can't operate a flocculator at 500 hertz. Okay, so conclusions. Our goal is to reduce the concentration of the unflocculated primary particles. That's what we're trying to do in flocculation. Only similar sized particles can collide. And so as flocculation proceeds, there's two things happening. There's particles that are slowly growing in size as they're colliding with similar sized particles. And there's the poor unflocculated primary particles that are left behind and that have no one to collide with. So it's difficult to flocculate to a low residual turbidity, like the turbidity that's caused by those unflocculated particles. And finally, shear tears flocks apart or prevents them from attaching. And so that ends up being another important parameter in our